Alright, so I'm Keoderitz, and I'm presenting on the Rankine cycle. Sorry I wasn't here last week. Alright, so first thing we're going to do is go over the purpose of this experiment, and we'll come up with a process, and we'll look at a simple schematic to simplify things. Also take a look at how the TS diagram plays in with this, look at the data that we gathered, and some results that are computed, some possible uncertainties, power comparison, and we'll wrap that up with a conclusion. Alright, so the purpose of the Rankine cycle is to generate electric power from working fluid steam. So the steam enters and it's expanded, and there's a pressure drop and a velocity increase which spins the turbine and creates the electric power. So we tested this with the light bulbs that are on the wall over there. We had a half load and a full load, where the half load was 8 light bulbs and the full load is 16 light bulbs. Okay, so the process of this experiment pretty much start with pumping water to the boiler, and then the boiler is going to heat up the water and put it to steam through the turbine. The turbine will then have a reverse weighted adiabatic expansion. The steam will be rejected into the leftover steam will be sent to the condenser, where then it will be then turned into liquid, and it will enter through the pump, and the process will go again. Okay, so this is a simple schematic of that. Right here, the pump, you see there's work in, the water is then heated until it turns to steam, goes through the turbine, that creates the work out of the turbine, and then exhausted into the condenser, heat is kicked out, and then back to the pump. Okay, so same thing on the TS diagram, but you can see with the bell curve that water is pumped isotropically, and then heat the water to its boiling point, then vaporize the water into dry steam, superheat it, and then isotropic expansion of steam in the turbine, and then condensing the turbine's exhaust steam back in the water, cycle repeats again. So, okay, this is the data we took. We did 2 half-load runs and 2 full-load runs. And the time differences for the half-load runs they weren't too similar. We had 119 seconds and 138, whereas the full-load ones are only a second apart. And for most of the calculations in this, we used the half-load run. And so they came up with an average time of 128.8 seconds. And the temperatures, pressures, RPM, and power, those were all fairly similar. So useful equations for this experiment: pump work in, heat out, turbine work out, turbine efficiency. And these all deal with the certain enthalpies that we had to find. So finding the enthalpies, had to do interpolation based off of the steam tables from the temperature and pressure readings that we got off of the machine from the data, and we had to find 1 through 4 first, and then from the previous equations you can use that to find the pump exit enthalpy. So we found all these. Alright, now that we had the H's, we could solve for mass flow rate, work in, work out of the turbine, heat in, and heat out. And for mass flow rate, we did density times volume over the average time. That gave us 0.0232 kilograms per second. Work in used the specific volume, which was also interpolated. And that was pressures times mass flow rate. Work out of the turbine was mass flow rate times H2 minus H3, 11,500 watts. And we found the pump enthalpy, then we can find heat in, mass flow rate, H1 minus enthalpy of the pump. And then heat out, we did mass flow rate, H3 minus H4, 50,000 watts. Okay, so for the efficiency of the turbine, use the equation off of given equations. came up with 5.45%. I don't know how accurate that is, but I tried it a few times. A little confused with it. Cycle 9% and ideal cycle 14. Okay, for uncertainties, there could be interpolation problems because the answers could vary, and some of the tables can differ. If they're older or newer, some of the values may be a little different. The readings from when we were getting the data, I know the pressure gauge, is a dial, so the reading can be off the resolution. And from the circuit analysis, the actual is plus minus 0.2%, and the turbine work output is actually plus minus 5 watts. Okay, for the power comparison, what we calculated from the half load was 11,500 watts. But when we put the multimeter on it, we got 395 watts. So this showed that the load we were testing only was 395 watts, but we were capable of 11,500. So we could actually handle much more. And to wrap that up, we're creating electric power from steam, and there are certain uncertainties that can occur through this, and power can be compared by directly comparing the calculations with the multimeter wattage output. And any